Everyone, my name is Lili Wen. I'm a senior engineer from China Guangxi Academy of Marine Science. It's a great honor to present our work on remote sensing monitoring and warning of harmful algal blooms in marine aquaculture areas at ECNO 2025. I'm so apologize I can't be here in person. However, I'm excited to share our findings with you guys. Let's start with why this matters. Harmful algal blooms pose severe threats to marine aquaculture. They reduce dissolved oxygen in water, threatening the survival of farmed organisms. Some algae produce toxins that accumulate in aquatic species, leading to mass mortality beyond direct losses. HAPs disrupt ecological balance and deteriorate aquaculture environments, hindering growth and causing significant economic damage. This is why monitoring and early warning are critical. Has emerged as a game changer here. Its advantages are clear. It enables multiple parameter collaborative monitoring, large-scale synchronous observation, and continuous dynamic tracking of HAPs, all essential for early warning and rapid response. Economically, it significantly reduces monitoring costs and minimizes losses from HAP outbreaks. It also provides very detailed data to support disaster assessment, optimize emergency strategies, and ensure ecological security. Importantly, remote sensing covers vast sea areas, capturing the full picture of habit evolution. Because sometimes traditional methods can't match. However, a key challenge is lack of unified technical methods and standards for remote sensing-based HAP early warning. This inconsistency makes it hard to meet the demands of emergency response. To address this, our study developed a set of guidelines to standardize the process, from remote sensing judgment of HAPs to on-site verification, risk assessment, and warning issuance. Let's go through this guidance step by step. Firstly, the monitoring and warning process. It covers 4 key stages, including data collection, processing, analysis, and field verification, all designed to ensure operational standardization. We've defined data processing standards, including satellite and sensor data acquisition methods, and pre-processing steps like denoising and registration to guarantee data quality. For HAP identification, we established the classification models based on spectral characteristics and spatial temporal patterns, helping identify high-risk algae. Finally, the warning release mechanism integrates remote sensing and field data with graded standards and clear channels for information sharing. Now, let's look at this figure. It illustrates the application of remote sensing in monitoring and early warning of HAPs in mariculture zone. The process is like data acquisition, interpretation, identification of potential HAPs, and on-site verification to issue early warning. It highlights that remote sensing technology effectively enables preemptive detection of HAPs. Next, I want to introduce data acquisition and pre-processing. What data do we need? We rely on ocean color satellite images from sensors like MODIS, Seaweeds, Maris, Guangxi, and Guangxi. We collected the target aquaculture areas. For reliability, spatial resolution must exceed 1.1 kilometer and the temporal resolution should ensure at least one data update every 2 days per satellite. The spectral range covers 400 to 1100 nanometer, including red, green, blue, and infrared bands. Processing is crucial to turn raw data into usable information. We perform radiation correction using relevant formulas, converting digital values to true sea surface radiance. Atmospheric correction, detailed to each satellite type, yield corrected reflectivity and normalize the water radiance. Geometric correction fix image distortion using ground control points. Finally, data splicing merges overlapping images for full coverage and trimming bolts on key monitoring areas. Let's move to data interpretation and analysis. We focus on two core parameters, chlorophyll concentration and sea surface temperature, SST. Chlorophyll spikes during HAP outbreaks, directly reflecting algal biomass, make it a core indicator. SST, a key environmental driver, and directly shows if conditions are suitable for HAPs. For SST retrieval, we use long wave and short wave algorithms calibrated with meteorological data to reduce atmospheric errors. For chlorophyll, we use linear and nonlinear regression models, optimized with field data, multi-center fusion, and seasonal adjustments. And then, for identification for potential HAPs, we combine three criteria: chlorophyll concentration, SST, and sea color. From this, we extract key information, including distribution, scope, area, algal species, and movement chains. The last part is ensuring HAP warnings. We classified warnings into 3 levels based on risk. Level 3 is low risk. HAPs cover 5 to 10% of the aquaculture area. Chlorophyll is 1 to 1.5 times above normal. SST rise 1 to 2 degree. Level 2 is medium risk, helps cover 10 to 20% of the area. Chlorophyll is up to 1.5 to 2 times. SST raise 2 to 3 degrees. Level 1 is the high risk, helps cover 20 to 30% of the area. Chlorophyll is up to 2 to 2.5. SST raise 3 to 4 degrees. In the end, these guidelines standardize remote sensing-based help monitoring and warning, enhancing early detection and response. By unifying technical methods, we aim to strengthen the mariculture industry's disaster resilience, reduce losses, and protect ecological security. Well, thank you for your attention. I welcome your questions and collaborations. Let's work together to protect marine agriculture and ecosystem. Thank you. Bye.